The century debate between Albert Einstein and Niels Bohr. At the beginning of the 20th century, two influential schools of thought emerged in the field of physics. One was Einstein's theory of relativity, and the other was quantum mechanics, which was formed by the joint efforts of multiple masters led by Bohr. Assuming that you have watched the previous videos and can fully understand what I am saying, then I can continue telling the story. The cause of the matter comes from Bohr's claim that the theory of quantum mechanics is complete, that there is no causal relationship in the microscopic world, and that humans can never obtain definite results in the real world. Einstein held an opposing view, believing that God does not play dice, which meant that the world is not random, but Bohr replied, "Einstein, stop telling God what to do." Einstein and Bohr had a three-round debate. For the first time, at the Fifth Solvay Conference in 1927, Bohr believed that quantum theory was based on the uncertainty principle and a Copenhagen interpretation, and proposed the principle of complementarity in quantum mechanics, which means that the determinism in classical physics and the uncertainty in quantum mechanics cannot be simultaneously considered when describing microscopic particles. At this point, the theoretical system of quantum mechanics is complete and the logic is self-consistent. Einstein did not agree and proposed a thought experiment, slit experiment, to prove the internal contradiction of quantum mechanics theory. In the double slit experiment, a large mass baffle was set up with the aim of not changing the wave function of particles, and then particle waves were emitted, note, not individual particles. Then adjust the intensity of the particle wave so that only one particle passes through the slit at a time. When a particle wave diffracts, the momentum of the particle changes is transferred to the slit. By measuring the momentum change of the slit, it can be determined which slit the particle passes through. In this process, particles exhibit both wave and particle characteristics, and can accurately infer their trajectories, violating Bohr's complementarity and uncertainty principles just proposed. Bohr's reply, narrows are also considered as part of quantum systems. Due to the uncertainty principle, when measuring the momentum of a slit, particle waves will be subject to uncertain interference, and the interference ripples that originally appeared on the receiving screen will disappear. Okay, Einstein was very convinced by this explanation. The second time, at the Sixth Solvay Conference in 1930, Einstein brought the thought experiment photon box. Suppose a box is filled with photons, and the box has a door that can be opened at a fixed time. Each photon is emitted outward, and then the door is closed. By measuring the mass before and after this box, the mass and energy of photons can be calculated, and the time interval is determined. Therefore, the accurate time and energy of releasing a particle can be measured simultaneously, which contradicts the uncertainty principle. It is said that upon hearing this, Bohr's face turned pale and stunned, because once Einstein's thesis was correct, the theoretical edifice of quantum mechanics would instantly collapse. After a whole night of contemplation, Bohr was once again in high spirits the next day. He took out a sketch to indicate that if the mass of the photon box was measured using a spring scale, then when the photon flew out and caused a change in the box's mass, the box would inevitably move in the direction of gravity. At this point, even if the measurement of mass is accurate, the clock effect inside the box will make the measurement of time no longer accurate, in accordance with the principle of uncertainty. Defeating Einstein with the theory of relativity forced Einstein to accept it. But this did not completely convince Einstein. The last debate between the two was in 1935, when Einstein, Podolsky, and Rosen jointly published an article titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" with the intention of exposing the incompleteness of quantum theory. This time, they still proposed an idea experiment, EPR experiment, in quantum mechanics. Two particles are entangled under certain conditions. If the state of one particle changes, the state of the other particle will also change instantaneously, regardless of how far apart they are, which Einstein called Spökkraftfernwirkungen, which contradicts the local realism that a complete physical theory should satisfy. Simply put, local realism means that events occurring here cannot immediately affect other physical realities beyond a long distance, and the speed of transmission must be taken into account. This concept is known as the Einstein-Podolsky-Rosen paradox. Bohr, who had already won 2 rounds, gladly faced the challenge. A few months later, Bohr published a paper with the same title, Can Quantum Mechanical Description of Physical Reality Be Considered Complete?, believing that any observation would cause enough physical interference to prevent Einstein and others from refuting quantum theory. From then on, according to Bohr's interpretation, quantum mechanics cannot be proven by any practical experiment. Unless the logic of quantum theory itself is flawed, it can no longer be defeated by any doubt. The Huashan debate in physics has yet to be decided, but it has been talked about by future generations. Einstein and Bohr passed away in 1955 and 1962 respectively. It is said that on the night before Bohr's death, he also drew Einstein's photon box on the blackboard. The great debate involving physics and philosophy of science is still ongoing, and the next time we will delve into the quantum entanglement that confuses Einstein.